Hi guys, this is Rohit here, and today we are going to take it right from where we left in the last session. So last session was about descriptive statistics, and this session is called inferential statistics. So today is inferential statistics part 1. So inferential statistics is basically divided into two parts, right? So today we are going to cover the first part, and then in the next session we are going to cover the second part. And this is just directly after what you have studied. So basically everything is in just continuity with the descriptive stats section. So with inferential stats, what are we gonna do? So descriptive stats was where we talked about mean, median, mode and all of those measures and basically how they're useful and when they're useful. We talked about standard deviations. So those are descriptive stats, right? Because they kind of help us describe the data that we have at hand. So that's awesome. That's perfectly fine. We understood all of that. So why inferential stats? Inferential stat is well, we want to kind of not only describe the data, but we want to infer from the data, right? So that's why inferential stats. So descriptive stats was basically we could describe our data. Hey, look, this is how our data looks like. This is how the data is distributed. This is mean. This is the standard deviation. This is how the variation in the data is. Inferential stats goes beyond the step and it says that, hey, I think this is my data. Now let me try and infer what is probably the price in this particular neighborhood, right? Because we are talking about prices of houses in New York. So now if I want to infer prices in a particular neighborhood, or if I want to infer probably, if I take 15 samples out of this entire Brooklyn house out of this entire New York City, I take 15-20 houses and I want to just based on those 15-20 houses, if I want to infer the entire prices about the entire New York City, right? So if I want to do all of those kind of things when I'm trying to just take a small sample of the data, because at the end of the day, understand this, right? Because we are talking about this problem where we are trying to estimate prices in New York City, right? So that was John's major problem, right? When John started, he basically had to figure out how to allocate his funds. Now, to do that, he has to obviously the most essential way most basic thing you can do is basically go and collect every house data possible in New York City, like every house possible, right? At every whatever 50-60,000, 1 lakh, 2 lakh, I don't know what is the amount, but you have to collect the data from all the houses, and based on those houses you can draw your inferences, right, about what is the kind of fund that you would want to allocate. Now the second option is basically John doesn't really have that much time. So what he'll do is he'll probably take a sample of 15-20 houses, and from those 15-20 houses he will try and infer something which is generalizable about the entire houses of New York, right? So he would gonna select those 15-20 houses strategically, and then he's gonna do some strategic inference on that, and based on those inferences he's going to conclude something about the entire houses in New York, right? So that is the whole concept about inferential statistics. Now inferential statistics is a big I would say it's a very long course in a normal university curriculum, right? So it's actually a semester long course that is there in inferential stats, specifically everything that we're going to cover here, right? So starting from descriptive stats to all the way inferential stats, everything is in a real university course is a semester long course. So now that we are trying to cover all of that in a very short and concise way in probably 2-3 hours, what that kind of does is two things. One is obviously it makes it very brief and concise for you to consume very easily, right? But at the same time, there's a slight problem with all of this concising, right? Which is that there would be parts which would seem like, hey, this is probably moving a bit too fast, or this is probably moving a bit too slow. So I'll do at my end is basically try and go as slow as possible on each of the topics so that you kind of get the links. But obviously there would be certain things which are probably not clear in the first run. So this particular lecture is something that you would probably want to kind of view at probably a slower speed, or probably view multiple times, or stop and then look up things on Google, understand a bit more, and then look back. So that's something that you might want to do in this particular lecture. So that's a heads up. Apart from that, this is probably one of the more tougher, I would not say tough, but probably one of the more complex parts of your entire curriculum. Everything up from here, right, after inferential stats is going to be absolutely easy. So just hold on with me with this one. You understand this, it's going to help you for your lifetime, right? And this is something that is very, very critical for you to understand. And obviously, if you have some kind of statistics or a maths or engineering kind of a background, you probably know half of this already, or probably fully entire thing already. But if you do not know, don't get afraid. If you do not, you're not from maths background, and that's perfectly fine. We are gonna try and talk about very simple examples as that every one of us can understand and relate to. Given that's the context, now let's get started with inferential statistics. So programs so far, obviously you have been introduced to Python. That's awesome. If you are not still introduced to Python or you're not familiar with it, not probably right time to kind of go ahead and jump into inferential statistics. I would suggest go back, get that done really very well before you kind of go ahead and try and jump into this piece. You can do street fighting with Python. Yeah, you can do. I'm guessing all of that is part of it. And you also know what are the machine learning processes and various stages in it from a 30,000 feet perspective, right? So yeah, you have that overall idea of where machine learning is all about, what is it all about, what differentiates machine learning from rule-based systems and all of that thing. So that's a fairly good place to be in. Also, you know about what is not written here is you also know about descriptive stats. So you understand what is mean, median, mode, what is standard deviation, interquartile range, all of that, right? So that's awesome. So now agenda for the day is first we get introduced to this concept of probability, then we understand this concept of sample population, then some random terms. I want PMF, PDF and CDF, and then we talk about two probability distributions, binomial and normal. So first up is introduction to probability. So John is still searching. Buying a house is obviously no joke. There are a number of factors that need to be considered while selecting one particular house, obviously, right? One such factor is neighborhood. Yesterday we learned that Brooklyn is one of the 5 boroughs in New York. So New York is basically split into 5 different regions per se. So Brooklyn is one of them, and then there is Manhattan. There are a couple of them, I forgot the names. Manhattan is basically the one which is the most expensive place in New York. But it has so it has basically the several neighborhoods, right? So neighborhoods are basically these small sub-regions within boroughs. And interestingly, like in any big city, some are rich, some are poor, some are in the process of being gentrified, some are actually culturally diverse. So yeah, there are a lot of variations in the different neighborhoods, right? So that's a message from that particular point. And John has displayed interest in several such neighborhoods, and in addition to his 1460 observation, you remember this 1460 observations from previous session, right? So John was looking through New York prices and he found this 1460 population, right? 1460 houses that he had, and we found out the mean of those, we found the median of those. You remember that deal, right? So we had looked at this 1460 houses and their corresponding prices, and he found out about neighborhood of each and every one of them. Fair enough, this is what we have done. So this is one of the neighborhoods, right? So I don't know what this is called, but this is something that we can see from the map is adjacent to the sea. So now John is curious. So by just looking at the data, John sees this interesting house prices in a neighborhood called Old Town. So he's curious about this neighborhood and wants to see for his own amusement that if one was to pick a house at random, what were the chances that the house would be in Old Town, right? So again, so John is now curious about these different neighborhoods that he can find, right? John is curious about finding a house, and he comes across this particular neighborhood, and he sees that there's one particular neighborhood called Old Town. So now he's curious that what are the chances that he might end up in this particular neighborhood, right? So this whole thing, that the basic word that I just used right now. So what is the chance that you would end up in that particular neighborhood, right? So this word chance is the precursor to every concept in probability, right? So now let's introduce ourselves to the concepts of probability, right? So there are two basic approaches in considering probability. So the first one is frequentist approach. So it is defined by the frequency of the event based on the data. Sounds obvious, right? You would obviously define a frequency based on frequency of data. This doesn't sound. Let's understand that in a real world example. And there's a Bayesian approach which is defined by combining previous experience about the event and the current data. So going forward in the day, we will be discussing mostly about the frequentist approach. That's perfectly fine. But let's understand what is frequentist and Bayesian, right? Sounds very hodgepodgey out there, right? So let's look at the example. Assume a situation where you have lost your phone, right? So now how would you kind of try and figure that lost phone? So there are two options for you. One is you would try and give a call on that phone, right? And based on where the sound of that ringing phone is coming from, you would try and guess that, right? So that is a frequentist approach, right? Based on you give it a call and you try and see, hey, the sound is coming from this. Probably there is a chance that this sound is coming from sofa. There's a chance it's coming from the bedroom. So the chance for coming from sofa is 30%. If it's probably 50% chance that it's coming from bedroom and 20% chance it's coming from the kitchen, based on the sound and how you hear it. So you can kind of give probabilities to the different locations. That's one way you can figure out where your phone is. Now the other option is you are like, hey, I think I remember what happened last time. Last time I had kept it in the fridge for some reason. You had kept it in the fridge and you remember, hey, there was fridge, and the time before that I had lost it in the kitchen itself, right? Somewhere in the cupboards. So now you know that probably yes, given those two information, I can definitely say that this is also the third time that I would also lose it somewhere in the kitchen, probably for sure, right? And you probably give it a 90% probability given your last experiences. So that is a Bayesian approach. So you have knowledge about what you did last time, and based on that understanding, you can basically predict that probably this time also it would be on kitchen. That's your Bayesian approach. The frequentist approach was you kind of give a call, and based on where the intensity of the sound and all of that, you kind of give probabilities to each other. So there's no previous knowledge that is involved, right? So that is the basic concept of frequentist and Bayesian. And as we say, in this particular lecture, we are going to concern mostly about frequentist approach. We are going to touch small basics of Bayesian, but that's about it. We are not going to go into details of Bayesian approach at all. We are just going to stick to frequentist. So now basic intuition of probabilities, right? So let's say we start with a simple example, right? So the first example is that of a flipping of a coin, right? So flipping of a coin, and intuitively there is a 50% chance that you would get a head, and there's a 50% chance that you would get a tail. Now this is because there are only two possible outcomes, right? So therefore we say that the probability of there's a head that would come up in the toss of a coin is 0.5. Probability that there would be a tail that would come up is 0.5. And probability can roughly be described as the percentage chance of an event or a sequence can occurring, right? So you would flip a coin, and there's a 50% chance that it would basically be head, and 50% because it could be a tail, right? So this is very simple, right? You kind of understand this, right? You toss a coin, it could only be only two outcomes there, right? So it could be a head and it could be a tail, and there's no bias against head or a tail, right? Had been a loaded coin, right? Though, like the coin which there's probably a lot of mass on the head side, a lot of mass on the tail side, then you'd probably toss it, and then there's a lot of higher chance that it would land up on the head side or the tail side. If it was a biased coin, right? So those ones that you see in some movies, right? So if you have that, you would probably have you would probably have a higher probability of head or a higher probability of tail. But in a normal unbiased coin, which is basically the normal day-to-day coin, you flip it, it could be anything, right? It could be head or tail. So 50% chance of each of them, right? So that's why 50% chance. So that's why we say probability of head being 0.5 or probability of tail also being 0.5, right? So some basic terminology that we kind of need to clear up. First is experiment. Experiment is basically this whole concept that of coin tossing, right? So flipping a coin, right? So that is that thing that is what we call as an experiment. So this coin tossing event is basically an experiment where basically these are uncertain situations which could have multiple outcomes, right? It could be a head or a tail. So this whole experiment thing is coin tossing, right? You want to do 10 experiments, meaning you want to probably do 10 times you would probably want to flip your coin. Next is outcome. What is outcome? Outcome is basically the result of a single trial. Okay, so basically one experiment or one trial, whatever you call it, the result of that is basically your outcome, right? So basically the first experiment you would have head or a tail. Now what if you have head, that is your outcome. In the next experiment you again toss it and it's again a head, and that's your outcome, right? So that's the second outcome. Event is basically one or more outcomes from an experiment. So And what is event? Event is basically the possible outcomes, right? So there could be head, there could be tail. So those are two events that could happen for a single trial, right? So a coin toss, as I said, is an experiment. The outcome is basically the result of a single trial, and then event is basically the possibilities, right? So head is one possible outcome, tails is also one possible outcome. Now each of them, so at the end of the day, when you do an experiment, you would have one outcome, right? But there could be two events associated with it, and each of those events would basically have some probability associated with it, right? So events are associated with probabilities, but at the end of the day, when you observe, what you observe is just an outcome, right? So it could be head or it could be tail. It would definitely not be 50% head and 50% tail, right? It would be either be a head or be a tail. But both of those events have a 50% probability, right? So probabilities are basically before you observe the outcome, right? So once you observe the outcome, it could be basically either a head or a tail, right? So that's perfectly awesome. So now there are some basic rules that are associated with probability. At least these are universally common across whatever probability you're dealing with. You're doing with frequentist or Bayesian, doesn't matter. So there's some comprehensive rules. So the first is probability of an event would basically lie between 0. 0 is basically that nothing is occurring, right? So probability basically, if an event being 0 means that it's definitely not going to happen, right? So probably, I don't know, probability of, I don't know, some event, right? Any event. India probably playing FIFA World Cup in 2018, right? So that is something that you know had already happened. Even if you want to predict it for future, probably you would say 0, right? Because it's probably close to 0. And 1 is certainly occurs, right? So probability of India playing Cricket World Cup, for example, would be 1, right? Because you know that it's gonna play, right? So almost nearly 1, and probability of India playing FIFA World Cup is almost 0. So you can say that the probability of any event, right? Any event, basically any coin toss, be it coin toss, be India playing anything, be it finding a house within this particular range, any probability should lie between 0 and 1, right? So that's fairly understandable, right? 0 is basically where it's surely not going to happen. 1 is where it's surely going to happen, right? And it could be anything between that, right? So the next thing to understand is this particular notation called A bar, right? So A bar, A dash, whatever you call it. So for any event A dash is called as a complementary event, right? So which basically means that if A is basically signifying the event A would happen, A dash basically implies the event A would not happen, right? So basically if my event A is India playing World Cup, FIFA World Cup, and probability of that is 0, A dash is basically the event that India would not be playing FIFA World Cup, right? So A was the event India would be playing, and A dash is the event India would not be playing, right? So that's fairly easy to understand, and obviously you can understand if probability of A is X, then probability of A dash is 1 minus X, right? So it's just the opposite of it. So that's why it's called a complementary event, right? So A happens, the probability of it is X, A dash, the probability of the same is 1 minus X. So now for this example, let's say if A is the event, that number 3 will appear on when you roll a die, right? So then A dash would be the event that 3 does not appear, right? So which basically means that it could be any of 1, 2, 4, 5 or 6, right? So in this case, probability of A is 1 by 6. Now why is 1 by 6? So probability of A is, so we want, there's one possible outcome which is 3, and there are 6 possible outcomes, right? 1, 2, 3, 4, 5, 6. So because of that, the probability of event A is 1 by 6. Now probability of A dash is it would not be 3, right? So it could be anything else, but it's not 3. So in that case, our possible options are 1, 2, 4, 5 and 6. And out of possible options, 1, 2, 3, 4, 5, 6. So there are 5 possible options out of 6 total possible options, right? So 5 favorable outcomes out of total 6 possible options, right? In this case, there was one favorable outcome, the outcome that we want to measure the probability of, and there are 6 total possible outcomes. So that why the probability of A is 1 by 6 and probability of A dash is 5 by 6, and you can see that this is equal to 1 minus 1 by 6. Fair enough. So now some more basic rules about probability. So basic terminologies, I would say. So the next terminology is mutually exclusive events. So what are mutually exclusive events? Mutually exclusive events are basically those events that cannot happen together, right? So for example, it is impossible to roll a 5 and a 3 on a single die at the same time, right? So if your event is basically that it would be a 5 when you roll a die, or it would be 3 when you roll a die, both the events are basically mutually exclusive, right? If it's 5, it cannot be 3. If it's 3, it cannot be 5. For that matter, any of it, if you roll a die, any of the events, right? If it's 1, 2, 3, 4, 5 or 6, any of those 6 events are mutually exclusive, right? If one of them happens, the rest of them cannot happen, right? It can be only one outcome, right? Similarly with a coin toss also, heads and tails, right? Heads and tails are mutually exclusive event. If in a particular outcome, if in a particular coin flip there's a head, then obviously there cannot be a tail, right? So this is a concept of mutually exclusive events, right? Events which are exclusive, right? So only one of them can happen. If A and B are two events, then probability of at least one of them occurring can be represented as P of A union B, right? So now, what could be these events A and B? For example, anything, right? So for example, what would be India playing FIFA World Cup and India playing Cricket World Cup, right? So those are two different events, and then the probability of at least one of them occurring is given by probability of A intersection A union B, right? So let's get familiar with this terminologies as well. So this particular sign U, right? So this is basically representative of union, right? And then there's something that is probably we'll talk about it later, which is the sign of intersection. We'll probably talk about that in the later slide. So understand this, that A union, this basically sees this basically notation is of A union B. So if A and B are two events of two different events, then the probability of at least one of them occurring is given by probability of A intersection A union B, right? And the probability of at least one or two of mutually exclusive events is the sum of their respective probabilities, right? So if A and B are two mutually exclusive events, then the probability of at least one of them occurring can be written than P of A union B equals to P of A plus P of B, right? So what is that we are saying, that if A and B are two events which cannot happen together, then the probability of at least one of them happening is probability of first event plus probability of second event. For example, the same example, right? A and B be the event that we get the number 3 and 5 respectively when a die is rolled. Now the probability that we will get either 3 or 5 is basically the summation of their individual probabilities, right? So and it's very clear to understand. Why is this the case? So we are basically concerned about A intersection B, right? So A intersection B is basically 3 or 5. So there are two possible outcomes, 3 or 5. Any of them would be fine with me. And out of 6 possible outcomes, right? So that is 2 out of 6. So which is also equals to 1 by 6 plus 1 by 6, right? So this is for probability A equals to 3, probability B equals to 5, right? So probability of A in union B is basically probability of A plus probability of B, right? So this is PA plus PB. These are the two events, right? And we can see that this is something that holds, right? Because these two events are mutually exclusive, right? Mutually exclusive just that means that there's a probability of 0. So this is how you would say this, equals to 0 for mutually exclusive events. A intersection basically means that 3 and 5, both of them will occur, right? So that is 0, right? Because it's a single die roll. In a die roll, there can be only one outcome. So the outcome that it is both 3 and 5, that is 0, right? Because there cannot be two outcomes. There can only be one outcome, hence it is 0. So that is why you would say P of A intersection B equals to 0 for mutually exclusive events, right? So this is A union B, right? So which is 3 or 5. And this is A intersection B. This is opposite of union, right? So just remember this symbol as well. So this is opposite of union. So union is just like U, and this is inverted U. So A intersection B is 0, because what you are saying by intersection B is that there's 3 and 5, right? So this is 3 or 5, this is 3 and 5. And obviously 3 or 5 you can have, right? You can basically have either 3 or 5. But you cannot have 3 and 5 in the single die roll, right? So that's why it's 0, right? So in case of a mutually exclusive event, you can basically say A or B is nothing but A plus B, right? Which is awesome. We understand this pretty clearly now. So now, what happens in non-mutually exclusive events, right? So to understand what happens in case of non-mutually exclusive events, let's draw a diagram to understand that. So this is my probability A, and this is my B, right? So this is my event A, this is my event B, and my probability of A union B, this is my probability of A union B, right? So probability of A union B is basically given by probability of A. This is the entire circle, right? So now let me draw this circle. So this is probability of A. So probability of A plus probability of B, right? But what is wrong with this? Because if we are doing, so the probability of A union B is basically this entire area, right? So now if we are doing probability of A plus probability of B, this is the region that is, we are counting it twice over, right? So we are counting it here as well, and we are counting it this here as well, right? So it's part of A as well, it's part of B as well. Now if the entire area is A union B, we are basically concerned with the entire area, right? So if we do PA plus PB, we are basically overcounting this particular area twice. So that's why we need to subtract this area from, and this area is nothing but A intersection B, right? So this is basically the common area between A and B, and that's why it's P of A union B is basically P of A, which is this entire circle, plus P of B, which is this entire circle, minus this common area, because you have counted this twice over, right? You have counted this in A as well as part of B. So now you want to remove that. So that is why you want to remove this. Now you can clearly see that for mutually exclusive events, P of A intersection B is 0, right? So for mutually exclusive events, it's basically like this, right? So this is your B and this is your A. So this is A, this is B, this is A, this is B. So in case of mutually exclusive, you can see that probability of A intersection B is nothing but probability of A plus probability of B, and that's it, because there's nothing. Probability of A intersection B is 0, so there's no common area between them. So that's pretty clear. Awesome, we kind of understand this whole thing together. So now let's do this class activity, which is in case of 50 students, let's say 30 students play hockey and 25 students play cricket and 15 students play both hockey and cricket. So what is the probability that a randomly selected student from the class plays either hockey or cricket, but not both, right? So we are concerned about what is the probability that someone plays either hockey or cricket, but not both, right? So now let's look at this. So probability of A is basically 30 out of 50. A is basically the event that a student plays hockey, and B be the event where student plays cricket. So probability of A is 30 out of 50. Probability of B is 25 out of 50. So and probability of A intersection B, which is both cricket and hockey, right? So there is 15 out of 30, 15 out of 50. So therefore the probability that a randomly selected student plays either hockey or cricket is 30 by 50 plus 25 by 50 minus 15 by 40. So that comes out to be roughly around 40 by 50. So that is 4 by 5. So there's a 80% probability that a student plays either hockey or cricket, right? Which is awesome, right? Because you can already see out of 30, there's a lot of people actually playing either cricket or hockey or combine both of them, right? So obviously probability that a randomly selected student plays either hockey or cricket is probability of A intersection B, which is either hockey or cricket, and that is probability of A plus probability of B minus probability of A intersection B. Awesome. So we understand this concept of A intersection A union B. So now let's consider this example. So specialized university offers 4 different graduate courses: business, education, accounting, and science. So enrollment figure shows 25 of the graduate students are in each specialty. That's awesome. Although 50 of the students are female and only 15 are female business majors. If a student is randomly selected from the university's registration database, what is the probability that a student is a business or an education major? So what is the probability that a student would be a business or an education major, right? So now we know what is the number of students who are enrolled in business as well as education. So there are 25 students who are enrolled in business and there are 25 students who are enrolled in education major, right? So what is the probability that a student is business or education? So we are basically looking at 50 possible favorable outcomes, right? So there are 100 possible students, 25 in each of the 4 categories, and out of those we are concerned with 50 possible favorable outcomes, right? So 50 out of 100, which is basically 0.25 plus 0.25, right? Which is also the same thing, right? Business, if there's someone is doing a major in business, obviously he cannot do a major as well as in education, right? So 25 students are in different groups of business and education. So probability of business plus probability of education equals to 0.25 plus 0.25 equals to 0.5. And probability that a student is a female or a business major is not mutually exclusive, right? Because there could be someone who is a female as well as a business major, right? Which was not the case earlier, right? Because earlier it was either you could be a business major or an education major, but now if you're a female, you could also be a business major, right? So those are not mutually exclusive events. So now what is the probability that someone would be female or a business major is that probability of female plus probability of business major minus the probability of being both a female as well as a business major. So that you can see is 0.5 because there are 50%, there are total 50 females out of 100 students. After that, the probability of business, which is same 0.25 because there are 25 students in each of the majors. So 25 students minus probability of female intersection business, right? So probability of people who are both female as well as business major, right? So that is 15 out of 100, so 0.15. So that comes out to be probability that a student could be a female or a business major is 0.60. So now some basic concepts. Again, as of now we have understood the concept of mutually exclusive events and probability union A, union B, A intersection B. That's all fine. So now there is a slightly new concept which we have talked about. It's called the joint probability, right? So which is basically this concept of intersection, right? So that's perfectly fine. So the concept that we are going to talk about is called independent events. What are independent events? Events which basically can happen. So now we are going to talk about an interesting concept which is after what we have learned. So we have learned as of now mutually exclusive events and A union B, A intersection B. So now the new concept is called independence of events. So as of now we have understood what it means for events to be mutually exclusive. So now we are talking about something called independent events. So what are independent events? Independent events are basically those events where the occurrence of one event does not affect the other event, right? So and they could happen together, right? So that's perfectly fine. They can happen together. These are not mutually exclusive events. Mutually exclusive events are those events which cannot happen together, right? So it cannot be 3 or a 5, right? But mutually, these are independent events. This just says that they can happen together, definitely, but it's just that the occurrence of one does not affect each other, right? So that's perfectly fine, right? So for example, if you roll 2 dice, right? If you roll 2 dice, and what is the probability that it would be 3 on and 5 on the other, right? So what is the probability? Now 3 can happen, these are 2 independent events, right? So 3 could happen in one die, 5 could happen in the other die, and they are not affected by each other, right? So your roll of, it's not like your one die is kind of dependent on the result of the other die. So if though that is the case, then probability that there is 3 in one die and 5 in one die can probably is just a product of the individual probabilities of 3 in one die and the 5 in one die, which is basically 1/6 and 1/6. So now let's consider this event. Suppose we are drawing one card from a deck of 52 cards, right? So in case of okay, before we go there, the concept behind independent events are, I kind of want to write that down because yeah. So independent events are basically those events which are where occurrence of one is not dependent on the other, right? So A and B can happen together. In case of mutually exclusive events, this was zero, right? Which is basically they cannot even occur together. In case of independent events, probability of A intersection B exists, and that is basically probability of A into probability of B, right? So these are two events which are not dependent on each other, right? But they can definitely happen together, right? So the same example as I gave you, you could roll two die, and there could be the event A is basically it's 3 in one die, and there's 5 in one die. That could definitely happen, right? 3 in one die, 5 in second die. So there are two different dies, and it could definitely be possible there's 3 in one die and there's 5 in one die. Now, what is the possibility of that particular event happening? So there is probability of A, which is 1/6. Probability of 3 coming up in one die is 1/6, right? There are 6 possible options, and 3 is just one of them. And probability of 5 is also 1/6. So probability of 3 in one die and 5 in the second die is basically 1/36. So that's the concept. So now if you apply the same logic out here, so suppose we are drawing one card from a deck of 52 cards. Now let A be the event that we get a card numbered 6, and B be the event that we get a card colored red, right? So we are basically talking about the red. So when we are talking about probability of A intersection B, we are basically talking about the card number which is 6 as well as red, right? So what is the probability of that particular thing happening? This is 1/26, right? So there are only two cards in red color 6, right? So which is the red of hearts and red of brick, right? So red of heart and red of brick. So those are only two possible options, and you can see that that's exactly what is happening. So 2 out of 52 is 1/26, and you can see the same logic applied here as well. So probability of A intersection B, right? So A is the event that is a card number 6. So how many possible options are there? So there are 4 possible options of card being numbered 6, right? So 6 of each of the spade, brick, and all of the possible options, right? So there are 4 possible options that the card could be number 6 out of 52 options. And the probability of B is basically B is this event where it could be colored red, right? So there are 26 colors, right? So there are 4 colors, 26 colors that are colored red, right? So there are 2 of each of heart as well as brick. So 13 each of red, 13 each of brick, and 13 each of hearts, right? So there are 26 cards that could be colored red. So 26 out of 52. So your 4/52 into 26/52, it comes out to be 1/26. So that's fairly understandable, right? So this concept of independence of events, right? So in this case, you can see that the events A and B are independent, right? So that we get a colored card number 6 is completely independent from the event that we get a card colored red, right? So they are not dependent in any which way. You can get a colored number 6, I can get a card red as well. There's nothing which particularly joins them. So now coming back to our friend John. So now John wants to check the probability of picking a house in Old Town. So this is nothing but number of houses in Old Town by total number of houses. So let's now go through the same thing in Python. So we import the libraries. So now what we do is basically the same thing. So first we figure out what are the total number of houses in Old Town versus total number of houses that he's looking at. So he's looking at somewhere around 1460 houses, and with that we basically see that his probability of picking a house in Old Town is 0.07, right? So roughly 7% of all the houses are in Old Town, which is fine, which is something we take it as it is. There's nothing we can talk about it. So that's obviously at random the probability of choosing a house. What does that 0.07 probability basically means? It just that says that out of all possible options of choosing a house, if we randomly choose one, there's a 7% chance that it would basically be in Old Town, right? So now what if John was extra curious? So having found out the probability of picking a house from Old Town neighborhood, what if John wanted to go further? So let's see what John wants to do now. So even though this would be pretty redundant, but when picking one by one, what would be the again probability of first picking a house from Old Town? So now John is kind of doing something slightly advanced than what he was told to do. So earlier he was just picking one house and he was saying that probability of it belonging to Old Town is 7%, which is awesome. Now he's saying, okay, I get that. When I pick it the first time, I get a 7%. Now that I've picked already one house from Old Town or whatever locality, I've picked one house. Now what is the probability that the second time I pick another house, what is the probability of that belonging to Old Town? Will that be still the same as my first probability? Will it change? That's a question that we need to understand, right? So if I'm picking one by one houses up from this data set, so first time I get it. First time if my probability of getting a house from Old Town is 7%. But now that I've chosen it and it's gone, what is the probability? Will the probability still be the same? So now this is the concept of conditional probability, and this probably might sound complicated, but let's break it down starting with an easy example. That's always the best way to do simple examples to get complicated concepts. So now let's say there's a bag and we are eating M&Ms. M&Ms, I don't know if you're familiar with chocolates, right? Basically that's it. So there are 10 chocolates in the bag, 5 are green, 5 are blue, right? So what is the probability of getting three blue candies in a row, right? So the probability of getting the first blue is easy, right? So it's 5 out of 10. So there are 5 green, 5 blue. So probability of getting blue in the first attempt is 5 out of 10, which is fine. When we pick the next blue candy though, we have removed this first candy. So now there are only 4 blue options available, right? Out of 9 possible candies, right? Because we have removed one. So now so let's draw this out and understand this clearly. So now let's understand this with a clear example, right? So let's say these are the M&Ms. So there are 5 blues plus 5 greens, right? So now obviously when I'm choosing what I'm trying to I'm concerned about the event A, where there are 3 blues picked in random. 3 blues picked consecutively. What is the probability of this particular event happening, right? So if we want a blue in the first place, right? If we want a blue in the first place, then the probability is very simple. It's 5 out of 10. Now once we have taken that blue, right, assuming this is now we want the second blue. Now we want consecutive blue, that means the first one is blue. So for that the probability is 5 by 10. Obviously if the first one is blue, then we are remaining with 4 blues plus 5 greens, right? So there are 9 possible options, and out of those 9 we want to choose 4, right? There are 4 possible blues that we can, and in the next iteration we will basically be left with 3 blues plus 5 greens. In that case, if the first 2 are blue, then obviously from this configuration, if we again have to choose a blue, the probability is 3 by 8, right? So, and these, as you can see, are independent events, right? So the probability of this particular event happening is 5 by 10 into 4 by 9 into 3 by 8, right? So that's the understanding that we need to develop, right? So that's pretty clear, right? From this example, it's not very tough to understand this concept. Now let's see what kind of thing that we are talking. When we say conditional probability, what is the thing that we are trying to say? So obviously, since we are calculating the probability of picking one blue candy and one blue candy and one blue candy, our final probability is, as we said, right? So 5 by 10 into 4 by 9 into 3 by 8, which comes out to be 8.3. So there's a 8.3% chance that we pick randomly 3 candies, one after the other. Out of them, there's 3 of them would be consecutively be blue. There's a 8.3% chance, right? That's clearly understood, right? So if you pick 3 candies randomly from this jar of 10 candies, the probability that all 3 of them would be consecutively be blue is 8.3%. So, okay, simple tricks. I think we have talked about this already also, which is basically whenever we have to verbally say and, like we did above, we just want to multiply the probabilities, right? And is basically the concept of A intersection B, right? and A intersection B, if they're independent events, they can be multiplied. So that's something that you need to remember. Whenever you are saying and, we have talked about this earlier. So A intersection B is what we are meaning when we are saying and when we are saying A union B, this is OR, right? So A union B is A or B, A intersection B is A and B, right? And obviously if it's A intersection B, it can be written as PA into PB if they're independent events, and this is equals to PA plus PB if they're mutually exclusive events, right? So that's a simple trick. Obviously remember this thing, that this is a trick and this is not a heuristic, this is not a rule, right? Obviously you understand when these conditions are valid, right? So in this case, if A and B are basically A and B, right? So that means intersection. So then you add them, then you multiply the probabilities only if they're independent events, right? Similarly, if it's A union B, A or B, then you add those probabilities, but under the condition that they're mutually exclusive. If they're not mutually exclusive, you have to add a term minus P of A intersection B, right? So that's a fundamental understanding that you have to keep in mind. So this is a simple heuristics that whenever it talks about and, just multiply them. Whenever it talks about or, just add them. But keep that in mind, right? This doesn't apply absolutely universally. So what is the probability of picking a green candy or a blue candy? And consider we have 7 candies. So let's do both of the cases. The first problem is, what is the probability of picking a green candy or a blue candy? So probability of picking a blue candy or green candy is mutually exclusive, right? So if you are taking blue candy and a green candy, it cannot be possible that you would basically have both of them. So obviously the answer is 5 by 10, 5 by 10, right? So that's perfectly fine. It's blue or green, right? And you can basically take one, right? Which is basically, obviously if I take anything out of those 10 things, right? Out of those 10 candies, that has to be either blue or green, right? So obviously that has, the probability of that being obviously is 1, right? So probability that any random candy that we select out of that jar would be blue or green is 1, right? Because obviously there are only 2 possible colors. So obviously it has to be 1, right? So that's obvious, right? So, and that you can verify from here as well, right? And the same thing that you can do out here is, the next question was, what is the probability? Consider that we have 7 green candies and 5 blue candies. What is the probability? So there are 12 candies all in all. And out of those 12 candies, what is the probability of picking one by one and without replacing 2 green candies or 2 blue candies, right? So 2 consecutive green candies or 2 consecutive blue candies if we randomly choose 2 of them. So then that's something that we know. So first we calculate 2 green candies, what is their independent event. So we know the probabilities of both of them. So that is 7 by 12 into 6 by 11, right? And 2 blue candies would be 5 by 12 into 4 by 11. And these are OR, so basically these are mutually exclusive events, right? It could be 2 green, 2 blue, right? So there's no way it can match in. So that's perfectly fine. So we basically just directly add them. And we get that there's 62 by 132. So that's perfectly awesome. We understand, we do understand this concept of what is the probability of selecting one after the other, right? So now you know that if John were to go and select one house from old neighborhood, whatever, old town neighborhood, the probability of him selecting the next house also from old neighborhood would not exactly be the same, because he has already chosen one house out of that set, right? So that's a concept that you need to kind of keep in mind. So now we need to talk about this idea of conditional probability as such. So conditional probability is, now say I roll a fair die and let A be the event of outcome that it's an odd number, right? So A could be, out of the 6 possible outcomes, there are only 3 of them which we are favorable, 1, 3 or 5. And let also B be the event that the outcome is less than or equal to 3. So possible options for B are 1, 2, 3. Now what is the probability of A? PA. What is the probability of A given B? Right, so that is, so again some notation that you see here, A and there's a pipe and then there's B, right? So what this means is probability of A given B, right? So let's kind of understand that notation as well while we are talking about it. So probability of event A. So what is the probability of event A? There are 3 possible options. out of that 6 possible total options, right? So 3 favorable options out of 6 possible options. We are fine with any 3 of these options, and there are 6 possible options. So probability of event A is 1 by 2, right? Now what is the probability of event A given B, right? So in our experiment we know that if event B has already occurred, so A given B basically means that what is the probability of A if I have told you that B has already occurred, right? So that is a way to interpret that whole thing, right? P A pipe B. That is basically means what is the probability of event A given B has happened, right? So if I tell you that B has already happened, so that means that the sum is basically less than 3, right? So then the outcome must be 1 of 1, 2, 3, right? So B has happened means the outcome is 1 of 1, 2, 3. So for event A, which is basically now out of event A was basically it could be any of the odd outcomes, right? So now what is the probability of A if I told you that B has already occurred? Which is simple, right? So the A intersection B, right? So there could be only be 1 and 3, right? So there are 3 possible outcomes given B has already happened. And now what is the probability of A, which is that it would be an odd number, right? So that is only 1 and 3 out of 1, 2, 3. Those are the only 2 possible outcomes that we are likely to, which would basically is the probability of event A, right? So probability of A given B is probability of A intersection B by probability of B. Now probability of A intersection B is there are 2 possible outcomes, and probability of B is basically there are 3 possible outcomes. So 2 out of 3 is our probability of A given B, right? So and that is fairly simple, right? So if I tell you that B has happened and B basically just consists of 3 possible outcomes, so 1, 2, 3 out of them, if I what is the probability of A? A is that the outcome is an odd number. So out of 1, 2, 3, 1 and 3 are basically the favorable outcomes. So that makes it probability of A given B as 2 by 3, right? So that's the concept of conditional probability. So conditional probability is something that we have already talked about this. So this is probability of A intersection B, and we are very familiar with this diagram by now. We have already drawn this in earlier. So this is A. This entire blue circle is A, entire green circle is B, and the area between them is A intersection B. So probability of A given B is probability of A intersection B by probability of B, right? So you are basically concerned about that. If I have told you that B is already happened, then what is the probability of A happening? Which is simple, right? So this is the probability of A intersection B by probability of the entire B, right? So that's perfectly fine. We understand conditional probability as well. So now what would be the probability of first picking a house from Old Town neighborhood and then again picking a house from the same neighborhood? So now let's find this out in Python, right? So old houses, houses in Old Town by all houses into houses in Old Town minus 1 by all houses minus 1, right? Because you have already picked out one house from Old Town. So that probability comes out to be bad. That is almost, that is 0.5%, right? 0.5% is the probability that your first house is also from Old Town and the second house is also from Old Town, right? So that's the understanding that you need to kind of develop here. Now let's do this through a class activity now, which is you toss a fair coin 3 times, right? Let's assume the 3 events to be independent. So what is the probability of each of those 3 heads, right? So H, right? So if you toss your coin 3 times, right? Let me draw this up for you. If you toss your coins 3 times, so 3 times means that the first time it could be H, the next time it could be H, it could be H as well, it could be HTH, it could be HTT, it could be HTH, HT, and so on and so forth, right? So there are total possible 8 outcomes, right? So out of these 8 outcomes, what is the probability that it would be 3 heads, right? So obviously the 3 heads is one out of these 8 possible outcomes, so 1 by 8. Now you can also calculate the same thing by H. Now each of the turns, the probability of H coming out is half, the half here as well, half here as well, right? So you can basically multiply half 3 times over and you would come out to the same conclusion, right? Let me write down all the possible outcomes for you. So there are, if you basically flip a coin 3 times over, there are 8 possible outcomes, right? As I've mentioned, HHH, HTH, HTT, HHT, THH, TTH, THT, TTT, right? So out of them, if you are just looking at HHH, that's one of the 8 possible outcomes. So the probability of HHH is 1 by 8. Now obviously also you can basically concur, you could have inferred the same thing also, because these 3 events are independent, right? Whether in the first coin it was head does not basically or the second chance it was head does not depend on whether it was head in the first time or not, right? So because these events are independent, you can basically multiply the probabilities of each of these events and you would come to 1 by 2 to the power 8, right? Now what is the probability that you observe exactly one head, right? So now so that's perfectly fine. So now what is the probability that you would basically observe one head, right? So one head is basically all of these events, right? Exactly one head is basically out of this possible options. So exactly one head is this, and this. So there are 3 possible outcomes where we basically see exactly one head, right? So the answer would be ideally 3 by 8. That you can verify just from the examples here, right? So this, and this. These are 3 possible outcomes. So that you can clearly measure by 1 by 8, 1 by 8. You can have basically calculated the probability. So this is the intersection of these 3 events. The intersection of this 3 event is summation of these 3 events because they are mutually exclusive. And each of the events you can calculate their probability. This is half, half, half. Again half, 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 and half, 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 right? So this probability of HTT is half into half into half, right? And similarly THT is half into half into half, and TTH is half into half into half. So that's why you come up with 3 by 8. So given that you have observed at least one head, what is the probability that you can observe at least 2 heads, right? So now let's A1 be the event that we observed at least one head, right? At least one head is basically there are 7 possible options. There's this one possible option TTT which we do not want, but at least one head is basically all this option. Now let A2 be the event where we observed at least 2 heads. Now at least 2 heads, there are 4 possible options. Then we basically can write P of A is 7 by 8 and P of B is 4 by 8 and P of B intersection A, right? So P of B intersection A is basically the common events between both B and A. Now this is basically all the 4 events are also part of A. So P of B intersection A is 4 and P of A is, so P of B intersection A is 4 because these 4 events are also part of A, right? So P of B intersection A is also probability of B. So P of B intersection A by probability of A, and then you can calculate this out to be 4 by 7, right? So out of 7 possible options, given that it's already said that it's at least one, and that means there are 7 possible options. And out of that, what is the probability that given this has happened, what is the probability that you would observe at least 2 heads, which is basically this thing, right? So out of these 7 options, there are only 4 favorable outcomes. So 4 out of 7 is what is the probability of A given B, right? So we understand this concept as well.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.